Hi everyone, welcome to week 3 of our biochemistry reviews. I'm just going to go ahead and jump right in. Last week we went over the rest of thermodynamics, and then we talked about amino acids a lot. And within amino acids, things like the side chains, pKa, things like the pi of the overall protein or polypeptide, drawing them, 1-letter and 3-letter codes, things like that. This week is a little bit of a continuation, more focused on proteins than just the amino acids. So yeah, I'm just going to go ahead and start with number 1. If I was able to acetylate a protein, what amino acid must be present in this protein? So the things that I think about when I'm approaching a problem like this are, first of all, what type of modification am I making? In this case, we're acetylating, okay? Then, what amino acid must be present? In order to acetylate something, we need certain groups. The way that I like to think about this is acetyl groups tend to be negative, right? Or like, I should say, they hover between neutral and negative. So my initial assumption when I'm approaching this is it's probably going to be a positive. So going through this, cysteine takes on a negative charge, serine takes on a negative charge, and threonine takes on a negative charge, and so it's lysine. Okay, that's the answer to number 1. This method does not work for every amino acid or for every post-translational modification. Okay, this is just a general rule that I like to think about of, does this make sense? Here's the full chart. My understanding is you only need to know the first 3. These 3 are fair game. The rest are not, you don't have to memorize for this course. So if I want to phosphorylate something, I need either a serine, a threonine, or a tyrosine. Does this make sense? Why? Sorry, I don't know why that scrolled. Okay. Does it make sense why we need one of these 3? Well, serine has an OH, threonine also has an OH, and tyrosine has an OH. Okay. So the rationale behind phosphorylation is we need an oxygen to attach the phosphate to make the phosphate group. Okay. Acetylation is fairly similar. Because of this negative charge, you get that positive. So does acetylation neutralize a positive charge? Yes, it does. Okay, really good question. And methylation, you need lysine or arginine. What's the kind of link between lysine and arginine? They both have nitrogen, and I'm going to go ahead and draw it as NH2. They both have amine groups at the end, right? And so it's really important to recognize these structural similarities because they really do help with the functional stuff, okay? All right, does anyone have questions about post-translational modification? Go ahead and type them in the chat. While I keep going, I'm going to go ahead and keep going to number 2. Okay, so if I scan a protein using UV-Vis spectroscopy and I see an absorbance peak at about 280 nanometers, what can we conclude about this protein? Okay, so 280 is one of those numbers they want you to memorize. Okay. Yes, someone said C. You're exactly right. It is that there's an aromatic amino acid present. The aromatics, which are tryptophan, tyrosine, and phenylalanine, these 3 show absorbance peaks near 280. Really, it's about like 250 to 300, but 280 is kind of the most consistent. Okay. All right. So really good answer. I'm going to go on to the next question: weighing a protein and finding a mass. All right, so the way to approach these problems is I have to ask myself, what's the mass of an amino acid? The average mass of an amino acid is 138 daltons, okay? Perfect, so someone said 110, and the reason for that is this is the average amino acid mass. However, our body makes some of these amino acids, and we consume some of these amino acids that are made in nature. So just logically speaking, what's easier to make? A small amino acid like glycine or a huge one like tyrosine that's got 2 rings to it, things like that, okay? The easier stuff to make, the smaller amino acids, tend to be more abundant and we tend to need more of them. So the average mass of small amino acids is 120 daltons, okay? But again, this isn't 110. So why is that? Does anyone know why we lose 18 Dalton or atomic mass unit when we use the number of amino acids? Water, perfect, yes. So in the formation of the peptide bond, we lose 18 Dalton, or 18 atomic mass units, in the creation of water in the hydrolysis. Minus 18 from water, perfect. So we would use 120 if all amino acids were abundant equally, and 110 for, just the average amino acids based on percent abundance. So when we do this, we get, let's see, 1685 over 110. I should get 15, right? The answer is B. Anyway, what do you think? Okay. So this is another one of those keep track of your units. Perfect. Yes, exactly right. We have to convert to Daltons. This starts as kilodalton, and down here it's in Dalton. So really it's 15,000, and what you end up getting is actually E, 15,318 amino acids. Okay. So yeah, just keep track of your units. Exactly right. All right. So now we're getting into the protein purification chapter. Okay. So if I were to run a native page at a pH of 7, which protein would I expect to travel furthest toward the anode? Okay. So again, so there are three things that I look for when I'm dealing with these. First is what kind of purification? Native page. Okay. Second, pH of 7. And lastly, which way are we going? We're going toward the anode. Okay. So I'm going to go ahead and start. What is native page? Native page is a gel electrophoresis that separates proteins based on charge to mass ratio, M to Z. Okay, so the lower mass, higher charge. Actually, I think if we just do, so the lower this number is, or the higher the charge to mass ratio is, the further it'll travel. Okay, depending on charge, of course, and that means the anode part is important. What is the charge of the anode of a native page gel electrophoresis? Anode is positive, exactly. This is one of the more unintuitive things. The anode is positively charged because it's where the anions go. So anions go to anode. That's how I think of it. Okay. So this is going to be one of those at a pH of 7. What is the charge of these 4 proteins? Okay. So I'm just going to go through very briefly, and if anyone wants to stop me for any reason, just type it in the chat and we'll go over it in more depth. But we know alanine does not contribute to pH. Tyrosine at 7 is going to be protonated, so it's going to be neutral. Histidine at 7 is going to be deprotonated, since its pKa is about 6, it's going to be neutral. Threonine, neutral. Serine, neutral. Lysine is going to be positive. Is everyone okay with that? Okay, great. So now alanine, letter B is just all alanine. Nothing contributes to pH, so it's going to be 0. Great. Okay. Alanine again does not contribute. At a pH of 7, glutamate is negative. Threonine is neutral. Aspartate is negative. There we go. And serine is neutral. So this is going to be a -2 charge. Over here we have alanine, 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 alanine. We have a -1, a -1, a 0, a -1, and a 0. So this is -3. Okay. So overall, our charge to mass ratio is 1 to 6 amino acids, which we could multiply by their masses to get the actual, but we don't need to in this case. For B, it's 0 over 4, or just 0. C is -2 over 5, and D is -3 over 9. Okay, so very briefly, I can tell you guys that since we're talking about going to the anode, we want the negatively charged things, right? So just right off the bat, I can tell you that A is going to travel the least because it's positive. Then B will travel some. And then between C and D, it's the charge to mass ratio. So -2 over 5 is -0.4. And D is -3/9, which is -0.33. In other words, it'll be D and then C. Okay, so an important thing to point out here is despite letter D having a stronger negative charge, it traveled slower than letter C. Okay, this is something that I think confuses a lot of students because they see a charge and they instantly think, okay, terrific, I know exactly what's going to happen. But it's not the case. Okay, you have to go to their masses. All right. Does anyone have any more questions about native page? Anything you want to talk about with this gel electrophoresis, trench mass ratio, any of that? Okay, awesome. All right, so jumping into number 5, if I were to run an SDS page at a pH of 7, which protein would I expect to travel furthest toward the anode? So right off the bat, there's a problem with this question. Does anyone know what that problem is? No? Okay, so I'm going to go ahead and point it out then. So SDS page, let's talk about the difference between SDS page and native page. Okay, so it's still a gel electrophoresis. However, SDS doesn't just separate them by charge. SDS coats all proteins with a negative charge, a fairly consistent negative charge across proteins, and so it only separates by size. Only separates by size. Okay, charge to mass ratio doesn't matter because they're all given a uniform negative charge. Okay, so again, we're going toward the anode, so it's positive, meaning anions. Great. Okay. The issue with this problem is this part right here. Okay, SDS page doesn't deal with pH at all because everything is given a negative charge. And so when you see this problem, either discount the pH or just, there's something wrong with it. Okay, and I wanted to point that out here, which is why this question is the way it is. So if we're only separating by size, if I can ever find my mouse again. Oh, got a question. When you're done, can you go over how you get the charge again on number 4? Absolutely, yes. Okay, so on number 5, we have 6 amino acids, 4 amino acids, 5 amino acids, and 9 amino acids. So only going by size, now D is the slowest, then A, then C, and then B. Okay, and it's just because B is the smallest, so when it's given that uniform charge, it's the lightest, it's going to go the furthest. Okay, is everyone okay with that? Okay. So now, jumping into getting the charge on number 4 one more time. So I'm going to go ahead and write them kind of down here where number 5 is, just for space, since I don't have much in number 4. Okay, there it is. So A, Y, H, T, S, K. K. So alanine does not contribute to pH, so it doesn't have a charge. There is something wrong with what I did for 4. Can anyone point it out to me? Something that I forgot. Every protein, or amino acid I should say, has an N-terminus and a C-terminus. Okay? Yes. Okay, so very briefly, the N-terminus, and it changed much, but the N-terminus is going to be protonated, so it's going to be positive. The C-terminus is going to be negative. So it's really easy to fall into the trap of, okay, this is the protein that I'm dealing with. Let's ignore the N and the C since, they don't matter. They do matter. In this case, they didn't because I picked a pH where they wouldn't, but it's something that I had meant to point out and then I actually forgot about it. And so, yeah, so I just really want to point that out to you guys. Don't forget your N and C termini. Yeah, okay. So coming back to just calculating the charge of these proteins. So you've got your N-terminus and your C-terminus. At a pH of 7, your N-terminus is protonated, and I know that that means that it's going to go from NH2 to NH3, and it'll be positive. Alanine does not take on a charge, and so I'm kind of ignoring it. That's why I crossed it out. Tyrosine goes from O minus to OH, but at a pH of 7, it'll be protonated, and so it'll be neutral. Excuse me. Histidine has a pKa, I'm sorry, did I say pH? pKa of 6, and so at a pH of 7, it'll be deprotonated. I know that histidine has nitrogen in it, and so I know that that means it's going to go from NH2 to NH3, or like N with 2 methyl groups and a hydrogen to N with 2 methyl groups and a positive char and 2 hydrogens, something like that. So I know that histidine is going to be positive since I know it has a nitrogen. Threonine has a pKa around like 12 or 13, so it'll be protonated. And so threonine being a hydroxyl is going to be neutral. Serine is pretty much the same, and our C-terminus has a pKa of either 2 or 4, in this case 4 since we're in a protein, and so it's going to be negative. Okay, does that make a little bit of sense? Okay, and then I just added them up, so I got plus, plus, minus, so plus 1. Okay, would histidine be deprotonated, so neutral? Yes, I'm sorry, I did that correct up there, and then I did it wrong down here. Yes, you're absolutely right. It would be neutral, and so this thing would be neutral. Sorry about that. Good catch. Okay, so and then I did that with all of them. And so it can be really helpful to just kind of get in the practice of going through and figuring out protonated, deprotonated, positive, negative, neutral, because it's a common question they love to ask because it's an easy question. Not an easy question, but it's an easy question to ask, okay? All right, so moving on to number 6. If I were to run an SDS page, which protein would I expect to travel furthest toward the anode and slowest? Okay, so this is the other thing that SDS page does. When you've got a polymer of multiple protein subunits, it breaks them down into monomers. Okay, so what I have here is, excuse me, is a 40 kilodalton monomer. Okay, great. So that's moderately fast. I mean, it's something. If I look at 120 kilodalton tetramer, so it's going to be broken into monomers. So a tetramer has 4 parts, tetra meaning 4. So instead of 120 kilodaltons, we're going to go ahead and assume that the 4 parts are all equal, and we're going to say each monomer is going to be 30 kilodalton. Monomers, okay? And so I want us to think about what we'd see on this gel. So you've got 1, 2, 3, 4. So maybe your 40 travels to here. Your 30 will travel to here, or your 30s, I should say. But it might be a really thick band, since now instead of having 1 monomer, you have 4 monomers. So it'll have a higher concentration than A would, and so it'll be a thicker band, but it'll travel to the spot where you would assume 30 would travel to. Okay, so that's something I want to point out because it can be a little confusing. Like, where will it travel? What will be different? It's just going to be a thicker band because there's more concentration. Okay, 20 kilodalton monomer in letter C. We're at a monomer. We're happy. 90 kilodalton dimer, meaning we have to go 90 over 2 to get to 45 kilodalton monomers. And again, with SDS page, we don't care about charges. We don't care about, charge to mass, anything like that. We only care about mass. And so we care which one's the lightest. That's going to travel furthest. So the lightest one in this case is going to be C. So it'll be the fastest. And then B, A, and D. Okay? Does that make sense to everyone why that is the way that it is? Okay, fantastic. All right, so now, oops, can I undo that? Okay, sorry. Okay. So number 7. All right, what kind of structure is an alpha helix? So someone is jumping in. Yes, it is a secondary structure. So I just want to very briefly go over the 4 since this is a common question. I want to make sure you understand this. And I also really want to point this out because in your next unit for exam 2, the structures are going to play a really big role. So I want to make sure you guys have this down. So primary is just the amino acid sequence. Amino acid sequence. sequence. Okay, so this would be like A, C, Y, K, and so on. Okay, your secondary structure is, things like alpha helices, beta sheets, things like that that are kind of large, usually based on hydrogen bonding, things like that. Okay, your tertiary structure is kind of other interactions based on intermolecular forces. Based on intermolecular forces. So this would be something like, let's see, a somewhat negatively charged amino acid side chain and a somewhat positively charged are kind of attracted to each other, but not very. So this wouldn't be strong enough to be considered a secondary structure since it's not a part of the motif, or I'm sorry, since it's not like one of these defined shapes, but it is something that will affect the overall structure of the protein and the protein folding. And so it's qualified, it's classified as a tertiary structure. Finally, quaternary structure is when you have multiple protein subunits, or I should say multiple polypeptide subunits. And we saw an example of this in number 6 when we were dealing with monomers and dimers and tetramers and things like that. Each monomer is a subunit, so anything that's a dimer, a trimer, a tetramer, and so on is going to have a quaternary structure. Okay? Does anyone have any questions about kind of structures? Okay, awesome. So number 8, what is salting in? And I have a graph later on, but I want to talk about it first. So salting in general is using an ionic salt, so something like sodium chloride, dumping it into your solution to make your protein more soluble. Okay, and it does have an upper bound, and that's why I want to talk about this here. So this, and I think I need to zoom out just a little bit. If it'll zoom, there we go. So this is pH versus solubility in milligrams of protein per milliliter. So what this is saying is for this protein with probably a pKa around, or I'm sorry, I should say a pi around like 5.2 to 5.4, this is how soluble it is when you have this amount of when you have this amount of salt in the solution. So when you have 1 millimolar of solution, or okay, I guess first I should start with why are they all U-shaped? Because when you're at your protein's pi, you're not going to be very soluble because you're pretty much uncharged and water is polar. Okay, does that make sense? I'll repeat it one more time. When you're at your pi, you're uncharged, and so you're not very soluble in water since it's polar, and the amount of salt helps a little bit, but ultimately you're just not polar enough for water. Okay? As you go more toward the end, so as you get more and more charged in either the positive or the negative direction, what happens is your solubility increases, right? So by adding a salt, what we're doing is we're kind of telling the protein, instead of forming these intermolecular forces, instead of forming kind of quaternary structures with all this stuff that's floating around with all the other proteins, form these intermolecular forces with the salt that we have here. Okay, and so it's kind of breaking apart the protein blob into these individual kind of protein pieces. Okay, and as you increase your concentration, that increases the effect that's happening. However, when you have too much salt, and that's what we see down here with the 4 molar, you're decreasing your solubility a lot, and that's called salting out. Okay? So coming to this graph, because I think it's a really good way to show it. So salting in is this green phase where you have these small kind of circles. Those are your salts, and then the orange is the protein. What's happening is you're seeing the salt interact with the protein just a little bit. When you reach kind of that peak at the top, you have each of the three protein molecules, I guess, kind of surrounded by their own couple pieces of salt that are reacting or that are interacting with them. and kind of keeping them away from the other proteins. Salting out is when you have so much salt that it's all stuck interacting with itself and it kind of leaves the protein on its own. Okay. So initially adding salt makes protein more soluble. Exactly. So I should explain this one. So this is salt concentration and this is solubility on the y-axis. So as you increase your salt concentration, you increase your protein solubility to a point. Okay. So first it increases until it reaches exactly right. Perfect. Yeah. And this is one of those topics that's really, really confusing and that it's really hard to understand at first. But once you get it, it kind of makes sense, right? What I'm doing to my water is I'm making it more polar, and so I'm forcing my proteins to interact with it, okay? However, at some point, it's just the proteins aren't going to be polar enough for the salt, okay? And so that's kind of where you reach that threshold and it starts getting worse and worse, okay? So the closer PI gets to pH, yes, I kind of want to put an asterisk on that because it's not, how do I word this? So we can see with something like the 1 millimolar versus the 5, increasing the salt increases the solubility up to a point, but they each still have their own kind of parabolic U shapes. And so does the 4 molar one, actually. It's not great, but it does have some solubility at a pH of like 4.8 or something. So in general, closer PI and pH are, the less soluble it is. The trend with salting in and out, I don't think has anything to do with that, but I'm not 100% sure. It's not something that's ever really talked about. It's a really good question, though. Okay. Okay, awesome. All right. So now that we've talked a lot about these protein questions, we're going to come back to protein purification. All right. So using ion exchange chromatography on some protein. So the things that we're looking for with ion exchange chromatography is, let's actually talk about it first. So I'm going to run my protein, if I can ever find my mouse, there it is, down this column. Okay. And what this column does is I've got this thing right here that's positive, and this thing right here that's positive, and this thing right here that's positive, and so on and so forth. Right, so let's say I have this protein that's really big and it's positively charged, and I have it attached to this negative charge that I don't like. Can I change that to red? I don't know how to do that. Okay, there we go. Yeah, so I have this negative charge that I don't like. So what's going to happen is, as my protein attached to the salt travels down the column, these negative charges will bond to the positive charges, and I'll attach new negative charges to it later on. Okay, so ion exchange basically exchanges ions, exactly how it's described. And so one of the things to think about is, what are we trying to replace? So most of the time you're trying to basically purify it, purify the protein. So what you'll see is, instead of, I want to replace this annoying anion with another anion that I actually like, you may see something like, I want to make sure that my protein is pure. So in this new column, I'm going to make sure that with my positive protein, I have a bunch of negative things in here. And so my protein stays in here and everything else gets flushed out, okay? And so that's the most common use of an ion exchanger, is just get the protein attached and then get everything else through it, and so the protein is pure, okay? So coming back to this question, if we wanted to use an ion exchange column on this protein, we've got its PI and we've got the buffer pH. So we don't know the exact charge that this protein will have, but we can guess what the charge will be, right? What do you guys think? Will this protein be positively charged or negatively charged? And that's a PI of 7. I realize that my circle kind of cuts through it. Okay, we have 1 for positive. Yeah, you're exactly right. This is going to be positively charged. Okay, and so if this is going to be positively charged, what kind of exchanger should I use? Should I be trying to exchange cations or anions? Cations, perfect. Yeah, so you're going to use a cation exchange column to purify a positive protein. Exactly. All right. All right. So number 10, more purification stuff. if we're using a polar loading solvent and a non-polar eluent or eluting solvent, either is acceptable, what type of chromatography are we using? So I want to talk about these 4 types of chromatography because I think they can be pretty confusing. Okay, so just off the bat, chromatography also pretty much always uses these columns. You can also use like thin layer chromatography, like you've done in your, I believe in your OChem labs, with just like a little sheet with some silica on it. And that's more solid, but for the most part, you tend to use these columns, and they're packed with this gel, and then some will have something in addition to this gel. So affinity chromatography, for example, will have these little, usually they're just called resins, basically just something that can interact with your protein going through it. And so affinity chromatography might be, you have a certain resin that is specifically attracted to the protein that we want to purify. So our square protein, and your resins will look like that to fit the square protein inside. And so exactly like you would expect, your protein that you're looking for is going to get caught in the column, everything else is going to go through it, and then at the very end you can use a different pH, you can use a ton of salt, something that'll just get this protein out. And it really depends on the protein that you're trying to purify, what you would use. And then that's how you would purify it, okay? That does not sound like what we're doing, so affinity chromatography is not right, okay? Hydrophobic interaction is, I don't want to say similar to affinity, but it basically creates this gradient where, I should draw this, let me draw this. So in the column, you create a gradient where this is really hydrophobic at the top, hydrophobic, and then this is not very hydrophobic, so it's more polar, not very hydrophobic. And what's going to happen is, going through this gradient as your protein comes down, as your various unknowns come down, I should say, is they'll get separated in terms of how many hydrophobic interactions they would have. So at the bottom is going to be the stuff that's not very hydrophobic, that doesn't interact at all with something like hexanes, with something like any of the just like really long carbon compounds. At the very top, you have the stuff that's really, really hydrophobic that will interact with that stuff. And so as it's traveling down, you get the not so hydrophobic stuff until you get to the hydrophobic stuff, okay? Do those two make sense, affinity and hydrophobic interactions? Because those are kind of the weird ones here. Okay, terrific. So now liquid and reverse phase are the exact same thing, but opposite one another. Okay, so I'm going to describe regular chromatography first, or I shouldn't say regular chromatography, but the most basic form of chromatography that's usually used. So usually you'll use, again, your silica gel, and this gel is really, really, really non-polar. Okay, and so the non-polar stuff will stick to it. Do I have that? I might have that backwards. I think this is actually polar. Yes, it is polar. Excuse me. If I can find my info. No, this is non-polar. I have that right. Yes. So this is non-polar for the most part. It'll interact with your stuff. That's all we care about. So now what's going to happen is I load my protein here at the top. Okay. I also use something like chloroform, dichloromethane, something non-polar, basically. A non-polar loading solvent. Okay. So now my really, really polar stuff is not going to want to travel in this non-polar loading solvent. So what I'm going to do is I'm going to pour in a polar eluting solvent. And what an eluting solvent does is it pushes your stuff down the column. Okay. So the polar eluting solvent is going to push the things that are polar down with it. Okay. And the non-polar is going to push the non-polar stuff down with it. Okay, so the question we have to ask ourselves is, if I have two things, or three things maybe, one thing that's really, really, really polar, one thing that's kind of polar, and one thing that's non-polar, and I load it into this column, Well, what I expect to see is 3 distinct bands, okay? One of the non-polar stuff, one of the polar stuff, and one of the really, really polar stuff, and then kind of gaps in between them, okay? So that'll be a gap, and then that'll be a gap, and it'll just be blank, okay? Because the eluting solvent should be polar enough that it'll really move your polar stuff down, and it won't move your non-polar stuff much at all. Really, your non-polar stuff is only moving because of gravity, okay? And then reverse phase is exactly like you would think it is. It's the exact opposite. So instead of a non-polar solvent, you use a polar solvent. Instead of a polar eluting solvent, you use a non-polar eluting solvent. So what we're looking at here is reverse phase chromatography. Okay. Does anyone have any questions about that? And if you guys couldn't tell, these are the 2 that I'm comfortable with. Is the polar band up top? No, I'm sorry. So when you're loading, wait, I'm sorry. In liquid or reverse phase? Because I was trying to describe liquid chromatography, and in this case, no. In reverse phase, the answer to this question, yes. Let me see. So this is non-polar, and it's because of the interaction between the eluent, the eluting solvent, and the protein. So the polar eluting solvent is going to move the polar stuff with it, right? The non-polar stuff is gonna not want to move with it because it's happy with the gel that it's in. And so as your polar solvent brings stuff down, it's gonna bring down the really, really polar stuff as much as it can. And then the non-polar stuff is gonna be stuck at the top. Okay, does that make sense? And then exactly like you said, in reverse phase, the non-polar stuff is going to be at the bottom because you're using a non-polar eluent. Okay, really good question. Okay. Whew, this is a fun one. When using size exclusion chromatography, why are large molecules the first to elute? Okay, so let's talk about it. So size exclusion chromatography is, again, you have this column, and inside of it you have these resins kind of all over. And these resins have tiny little holes in them. So I kind of want to like take that out and kind of expand that. So it's got this little hole through it, this little hole through it, all over, okay? And so what it does is as I load my stuff into it, the big stuff isn't going to be able to fit through this hole. So it's going to pass through this. The tiny proteins are going to get stuck here, and they're going to have to go through this resin, and they're going to get stuck here and have to go through this resin, and then stuck at the next resin, and so on and so forth. And it slows down the tiny stuff to get your big stuff out. So where is this most often used? So imagine you're doing a reaction and created this big carbon structure using something like ammonia because you needed a base in there, or something because you needed an amine grouping, okay? So when I use size exclusion chromatography, I get my protein or my long carbon or whatever it is that I'm looking for out quickly, and then the stuff like ammonia, the stuff that's really small, that's just kind of a reactant that I don't want, is going to get stuck inside of this column for a while until it gets out eventually over time. Okay, and so it's really used to get either the really big stuff or the really little stuff depending on what you're looking for. Okay, so coming back to number 11, large molecules cannot enter the pores of the resin. That's true. Do they get stuck at the top? No. Okay, so this one is kind of half right. There it is. Get stuck at the top? No. Okay, large molecules enter the pores. That's already wrong, right? They don't enter the pores, but they do go down quicker. Small molecules enter the resin and are trapped forever. They're not trapped forever. You can get them out, and they do come out. It's just inside of this resin, they have to go through kind of all over, all around, and then finally they get out. So it's just really good at slowing them down. Okay, and letter D, large molecules cannot enter the pores of the resins and go down the column outside, making it quicker. That's exactly what we're looking for. Okay, so this is pretty much the entire, like the protein purification chapter and the other chapter that we did, which was, yeah, just kind of post-translational modification and UV-vis spectroscopy, just more amino acid stuff. So what I went ahead and did is, because I know you guys have your exam tomorrow, is I made a couple of questions to review the rest of this unit. So if you guys have any questions you'd like to ask, the floor is absolutely yours. If you don't, I'm going to go ahead and just start working on these problems. And I'm going to go ahead and show you guys these problems so you can decide for yourselves, do we want to do this or do we want to just ask other questions? Let me zoom out a little bit more. Okay. So yeah, so these are the questions that we can work through if you guys want to. If not, and you have more specific questions, feel free. You want to use these questions? Okay. All right. And these are mostly just, I picked one or two from each topic just to make sure that we talked about them. I hope that you guys will either like understand this completely and you don't have to worry about it, or maybe you'll ask questions related to these once you see them, because this is, in my opinion, kind of some of the biggest topics of this chapter. Okay, so I'm going to go ahead and just get started then. Oh, sorry, I need to zoom in. Okay, so, okay. All right. What percent of cysteine side chain is protonated at a pH of 7.5 and a pH of 9? Okay, so this is going to be the Henderson-Hasselbalch equation, my favorite equation ever. So just to remind you guys, it's pH equals pKa plus the log of the conjugate base over the conjugate acid. Okay. One thing I want to point out is they'll usually give you a very specific pKa. So I know that cysteine is kind of about 8, but in this case, they want you to use the exact number because, I mean, it changes everything here. Okay, so how would I approach this? I'm going to say 7.5 equals 8.18 plus log A minus over HA. Okay. Just cleaning it up, I'm going to get negative 0.68 on the left equals this log of A minus over HA. And then when I take when I exponentiate, I believe, is the terms with logarithms are really confusing, I apologize. But when I undo the logarithm, I get about 0.209, okay? And that equals the concentration of A minus over HA. So how do I get to the percentage protonated? Okay, this is one of those tricks that I love using that a lot of people think is just not intuitive at all, okay? If we have, or I should say, the ratio of A minus to HA is 0.209 over 1, okay? Hope we're okay with that. Sorry, someone's typing in the chat. Do we add 1 to it? Exactly right. So what we're going to do is we're going to say, if I want the total, like HA plus A minus, so that I can figure out how much cysteine overall we've had in this, we're going to add that 0.209 plus that 1 to get to a total of about 1.209, okay? Does that make sense to everyone why we do that and like how we get there? Because this is, I think, one of the more confusing parts. Okay, great. So now it's asking for the percentage of the side chain, that's protonated. In other words, it's asking for HA over total. So 1 over 1.209 times 100%. Should add 1 over 1.209 is going to equal about 83%. 82.7 if we want to be exact. I'm just going to go ahead and say 83% for this one. Okay. So now we're going to do the same thing for a pH of 9. Hopefully this one will be just a little bit quicker since we know kind of what we're doing with it. Okay, so it's going to be 9 equals 8.9 equals 8.18 plus, and I'm just going to do that because I don't want to write it again. So we're going to get 0.82 on the left. We're going to undo the log, and so we're going to end up getting 6.61 equals A minus over HA. Once again, they put that under 1, and so the total is going to be 7.61. We want the percent protonated, so we're going to put 1 over 7.61. And we're going to get about 13%. Okay, so I want to pause here. 13%. Sorry, there's a question. I was following you up until that last step. Could you also just find the percent deprotonated and then subtract from 100? Absolutely, yeah. Totally fine. Sorry, when you say the last step, do you mean over here of the 7.5 one? Yeah. So all I did was I said, I know that my total is 1.209, and I know that, relative total, I should say, and I know that the 0.209 over here corresponds to my A minus, which means that my 1 has to correspond to my HA, and so I know that the relative amount of HA is 1 over the total of 1.209, and that's where I got that from. But exactly like you said, if I had put 0.209 over 1.209, I would have gotten about 17%, and I could have gotten to 83 that same way. Really good point. Okay. Okay. So there are two reasons that I included this. The first is to make sure that we're good with just pKa reactions with amino acids. The second is to make sure that we understand the idea of pKa and can check our work. Okay. So what I mean by that is below the pKa, I should expect, relatively speaking, to see a ton of protonated cysteine. And I see 83%. So I like that. Okay. Above the pKa, I shouldn't see as much protonated, and I see 13%. Okay. So again, and I've talked about this in most of my reviews, ask yourself, does this make sense? Okay. It doesn't have to be this huge complicated process. Just make sure that you understand above the pKa, deprotonated, below the pKa, protonated, and it can really, really help you, especially if it's a multiple choice exam and you have like, if it's letter A on a multiple choice exam and it's like 20%, 30%, 80%, 100%, you can instantly knock out the first two because you know you're below the pKa, so you need to be more protonated than deprotonated. Okay, does that make sense? Terrific. Okay, so now number 13. What is the PI of a polypeptide? And I just made it chemistry because I thought that'd be easy. Okay, so with this one, what I like to do is I go through and I say, does this contribute to pH? And I'm actually going to go ahead and include the N-terminus and the C-terminus to make sure I don't forget them. Does cysteine contribute to pH? Yes. Okay, cool. Does histidine? Yes. Glutamate? Yes. Methionine? Methionine does not. Okay, so for this question, I don't care about it. Isoleucine, also do not care about it. Serine, threonine, arginine, tyrosine. Okay, terrific. So now I'm thinking to myself, okay, the N-terminus is at about a pKa of 9. C, so cysteine, so about 8. Histidine is about 6. Glutamate is about 4. Serine and threonine are both around 13. Arginine is at about 12. Tyrosine is 10. Sorry, forgot that one for a second. And the C-terminus is around 4. And again, why is the C-terminus 4? Because we're in a polypeptide. The C-terminus of a regular amino acid. 2. Excellent. Okay, that is a very common question, or a very common concept they love to ask about. Okay, and again, what I do is I put them in ascending order. So 4, 6, 8, 9, 10, 12, and 13. And I draw lines down. Okay, and I ask myself, below the pKa, so below, at a pH of like 2 or 3, somewhere below 4, what's the charge of this thing going to be? So just going very briefly, nitrogen is going to be positive, and I'm going to do this over to the left so I have room. Cysteine is going to be neutral. Histidine is going to be positive. Glutamate is going to be neutral. Serine is going to be neutral. Threonine is going to be neutral. Arginine positive. Tyrosine neutral. So I see +3. Okay. Now between 4 and 6, if I can ever find my mouse, there it is. The N-terminus is still going to be positive. Cysteine is still positive. Histidine still positive. I'm sorry. Cysteine is still neutral. Still protonated. Excuse me. Glutamate is finally going to be negative now. Serine, threonine, and arginine are the same. Tyrosine is the same. Serine, threonine. I think, did I miss one? Yes, up here I should have one extra neutral. Excuse me. And then over here, arginine is still positive, tyrosine is still neutral. My C terminus is now negative, so now I have a +1 charge. Okay, and actually I'm going to pause right here for one moment. I think 2 weeks ago, or last week when we talked about PI, one of the questions I got was, can we assume that that trend is the same, up +2, +1, 0, +1, +2, and so on? And this is an example of a case where we can't. Okay, so because we have both glutamate or glutamic acid and the C terminus, whose pHs or whose pKs are about the same, we have to keep that in mind. And so we can't just go from +3 to +2. We have to, do the actual math for these. Okay. All right. So now the next part is between a pKa of 6 and 8. Okay. So the N terminus is still protonated. Cysteine still neutral. Histidine is now going to be neutral. Glutamate still negative. Serine, threonine, arginine didn't change. Tyrosine didn't change. C terminus is negative. So now our overall charge is neutral. Okay, and I could keep going through these, but for the sake of time, I won't unless you guys want me to. I know that my PI is somewhere between 6 and 8. In other words, the PI of this polypeptide is 7. Okay, does anyone have any questions about that topic? No? Okay, terrific. And again, if you want me to go through the rest of this, I totally can. I just don't want to waste your time since I know it's valuable. Okay. All right, number 14. At what temperature would this reaction be spontaneous? Okay. So this is, oh, and I should say, we are using, where's my mouse? Okay, there it is. We are using this information. Okay. So I'm going to use the delta G equals delta H minus T delta S formula here. Okay. I know that for this reaction to be spontaneous, G needs to be less than 0. So I'm going to go ahead and set that up. So 0, we want to be less than, oh, other way, right? Yeah, so we want this to be less than 0, excuse me. Delta H minus T delta S. Okay, and I'm going to go ahead and plug this in. One of the things I mentioned, I believe 2 weeks ago when we first talked about this, and want to remind you, is the standard units used. Delta H almost always uses kilojoules. Delta S usually uses joules. Okay, so just keep that in mind doing these. Okay, so I'm going to say 32,000 minus T times 117. Okay, I'm going to add that to the other side. 117 T has to be greater than 32,000, and then divide by 117. And so I get 273.5. Okay, T has to be greater than 273.5. Oh, I'm sorry, this is a negative delta H. We're going to treat it as positive just for convenience because I just realized I've missed it. Okay, so, and this is in Kelvin. Kelvin. In other words, it's basically the temperature has to be greater than 0 degrees Celsius. Okay, that makes sense. Okay, what is the equilibrium constant for this reaction? Okay, actually, yeah, okay, this is fine. So what is the equilibrium constant for this reaction? So what we're going to do here is we're going to say at 25 degrees Celsius, we know delta H minus T delta S. We're going to say equals, well, it equals delta G. We're going to go ahead and say delta G always also equals negative RT ln K. So we're going to set these two equal to each other and say 32,000 minus 25 plus 273, since we need to convert to Kelvin, 298 times 117 equals negative R, which again, R is unit dependent. It is 8.314 joules. I think it's joules per mole Kelvin. But the reason I say that is because joules. So since we have everything in joules, we're good. If we were to write it in kilojoules, we need to convert. 8.3 UN4, temperature is once again 298 Kelvin, and natural log of K. K is what we're looking for. Okay. I'm not going to go through all the algebra here. I'm just going to go ahead and let you guys know what the answer ends up being. Okay. Okay. And so the answer ends up being about 3.2. So again, I want to pause and say, does this make sense? So in number 14, we found that it's spontaneous at temperatures above 0 degrees Celsius. In this case, we're above 0 degrees Celsius, so this is spontaneous, meaning that K needs to be greater than 1. So this makes sense. Or like it works with what we know of it. If I had gotten a K that was 0.2, I would be saying, uh-oh, I did some math wrong. Let's go back and fix it. Okay, so that's just some things to keep in mind. Other things to keep in mind are, don't forget the negative charge the way that I accidentally did, because that does obviously change things. Would there be any issues here as far as delta G being standard or not? Let's assume that this is standard state, just for convenience. But it should, because K is only going to work when delta G is standard. Yes, I should have included that. That's my mistake. Standard. And I'll include that here. Good catch. Really good catch. Okay. Right. Why are many reactions coupled with ATP hydrolysis is our next question. We have too much ATP and have to use it. The reaction is very spontaneous and drives ATP hydrolysis. ATP hydrolysis is very spontaneous and drives other reactions, or ATP hydrolysis is not coupled with other reactions. What do you guys think? C, yes. C is exactly right. The ATP to ADP reaction is, the reason, by the way, excuse me, is you have these phosphodiester bonds. This is really, really, really unstable because your oxygens are all polar, so they're pulling at your phosphorus. Right, there we go. And so these phosphoruses, I don't know, are both really, really, really positive, and so this bond wants to break badly. And it wants to break so badly that it's delta G not prime, so the delta G in a standard biological system is somewhere around -31 kilojoules per mole, which is like a ridiculous amount. That's very, very spontaneous, okay? And so it drives a ton of other reactions really easily, okay? And the last question that I made for us, I don't know why it's not giving me the extra lines, is what is the equation of a Van 't Hoff plot? So this is, again, kind of getting at the same thing as number 15 is. Because we have two equations for delta G and delta G equals delta H minus T delta S, we can set these two equations equal to each other. Natural log of K. Divide both of these by negative RT, divide this, and actually separate them out. And so what we're going to end up getting is negative delta H over R times 1 over T plus delta S over R equals the natural log of K. We get this, Y equals mx plus B graph, with this as our slope. This is x, your 1 over T is your x, and this is your y-intercept. Yeah, so that's just something, again, just getting used to using these equations, understanding the delta G stuff. One thing that I realized I did is when I made this positive by mistake, I wanted to make sure that I viewed this. I lost that chance, so I just very briefly want to go over it. When you have, positive and negative delta H and delta S. Before I do, I want to make sure, does anyone have any questions? because this might take me a few minutes. Okay, so I'm just going to very briefly go over it. And again, this kind of comes down to, does this make sense? Okay, so if delta H and delta S are both positive, delta G is temperature dependent and it's spontaneous at a very high temperature. When you have a positive delta H and a negative delta S, it's always positive. Delta G is always positive, meaning it's never spontaneous. When it's flipped, so negative delta H, positive delta S, your delta G is negative, so your reaction is spontaneous. And finally, when they're both negative, delta G is again temperature dependent and spontaneous at low temperatures. Okay, so coming back to this problem, if I get rid of this positive, how will this reaction look? Will it be temperature dependent, always spontaneous, never spontaneous, spontaneous at high temperatures, low temperatures, whatever? What do you guys think? You guys cannot see that I highlighted that, can you? The delta H and the delta S, with those in mind. If both are negative, spontaneous at low temperature. So here we have negative delta H, positive delta S. Spontaneous at all temperatures, exactly right. Okay, and that's not a common question, but it's a good question that's asked sometimes with like number 14. Fairly common that you'll see, at what temperature would this reaction be spontaneous? You have to make sure that you're good at using the delta H and the delta S interchangeably very quickly, or else you have to do the math. And the math is much less fun. Okay, that is pretty much all I have for you guys. Oh, my camera turned off. That's it. If anyone has any questions, please feel free to type them into the chat. This is, for you guys to make sure that you're ready for your exam. So feel free anytime. Do you have advice on what to hone in on for the exam? Focus on, again, I don't know how it is online versus in person, but focus on really making sure you understand the concepts. I tried to give you guys some time-saving tips, like making sure that you knock out the easy answers, stuff like that. But really it's about, that's why. Hello? Sorry about that. I think I disconnected. I hope you guys can hear me now. What I was saying is focus on making sure you have your calculations down. Buffer stuff is really, really common. Make sure that you understand amino acid stuff, PI, charge at a specific pH, drawing them, 1-letter, 3-letter codes, those are also really common questions. Delta G stuff is, in my opinion, one of the more important parts of this unit. So those are things that I would really try to focus on. And obviously just making sure that you can solve any practice exams that have been posted will really help. The second question we got was delta G versus delta G naught. And I have that over here, so I want to just very briefly go over it. So delta G naught is the standard state Gibbs free energy. So all concentrations are at 1 molar. You're at about room temperature, so 298 Kelvin and 1 atmosphere. Delta G is the Gibbs free energy at any point. Delta G naught prime is the standard state in biochemical systems. So where the pH is about 7. And I believe I got this pretty much from your PowerPoint, just so that I can make sure I had it all accurate. So this is standard state. When delta H is consumed or produced, you have different equilibria. So this is your general equation for delta G naught between delta G naught and delta G. When you have delta G, when you have a standard state condition except for this pH, this is the simplified equation of just minus RT natural log of 10 to the negative 7, or plus, depending on whether you're consuming or producing protons, and that's, yeah, and that's just this is pretty much from your notes or from your PowerPoint. So I hope you guys have access to it. If not, send me an email. Do you guys have my email? I'm going to put in my email just in case. Do you recommend reading the book? The book can be very helpful. If you're confused on topics, I would strongly recommend going to the book because the book can always clarify things. I personally focus mostly on the PowerPoints just because I think that they're more exactly what the professor wants. I'm going to go ahead and stop recording since I don't think we have any more content questions.